It's in the context of a charging capacitor that we will discover why Ampere's law, as stated in the earlier weeks, is wrong. Now, if you remember, Ampere's law, as we stated it 2 weeks ago maybe, was the following statement. It was a circulation of the B field, which is given by the line integral around a closed curve of B dot ds, the closed curve C, is going to be equal to mu naught times the enclosed current. This was similar to Gauss's law, where you have the electric flux through a closed surface is equal to the enclosed charge over epsilon naught. And we applied this to a variety of problems and got some pretty good answers. But this turns out to be wrong. So this is the moment of truth. This law as written by Ampere does not take into account some very important considerations from topology. So one of the things that you need to worry about is what kind of surfaces does have as boundary the curve C. Now, all Ampere's law says is the current enclosed is given by the double integral of the current density dotted with the area element of that surface. It doesn't tell you anything else about that surface other than that the curve should be the boundary of that surface. So del here means the boundary of something. So that's all Ampere's law says. It doesn't tell us anything about the kind of surface S for which this is true. This is where Maxwell found that Ampere made a mistake. So let's suppose that we have a capacitor that's charging, and I'm taking the curve C. I apologize for this double usage of the word C. That's a capacitor, so maybe I should call that cap. With capacitance C, and then this here is the curve C that we're talking about here. Now, what surfaces can possibly have as boundary the curve C? Well, the most natural thing that we've been looking so far is just this planar surface, sometimes called the minimal spanning surface. The minimal spanning surface S1 is the surface that you will get if you dip the curve C in a soap film and you lift the curve out of the film, out of the soap solution, and you get this spanning surface. So that's the most natural thing that we've been looking at so far, and it's not bad that Ampere thought that was the only case. But the other thing you can do is you can look at any other surface. So for example, let's look at this this thing that looks like a jar of honey, for example. So you have this surface. Now you should think of this as a 3D surface. So I'll just draw some three-dimensional clues here. So even that has got as a boundary the curve C. What about now? Can this surface S2 be used? So I'll call S2 the non-spanning surface. Well, poor Ampere never thought of this possibility. Let's look at what happens when you charge the capacitor. Well, there's going to be a current I as a function of time. So that current is going to in turn set up an electric field between the plates of a capacitor that also change as a function of time. So the electric field E acts from the positive plate to the negative plate, and it keeps building up as time goes on. So these are the facts of life that we already know about a capacitor. The expression that we have for the current as a function of time is also well known. It's I naught, the initial current, times e to the minus t over tau, the time constant, which is r times c, and I naught is just e over r by Ohm's law. So initially the capacitor functions like a short, and all the current flows through it. So that's the current through a capacitor when the charging has just begun. You turn the switch on, and that's the current in the capacitor. So clearly current changes with time, And because current changes with time, electric field also changes with time. You can write expressions for all of these, and I'll put a problem of the week problem asking you to do that. So meanwhile, let's just look at what Ampere's law says. For spanning surface S1, Ampere's law tells us something very simple. You have the left-hand side, which is going to be, if you look at this thing, the magnetic field, you go around the loop, you do the usual things that you do with a magnetic field reduction. So you get B times 2 pi r. That's going to be the left-hand side of Gauss's Ampere's law, The regular Ampere's law is going to be mu naught times the enclosed current. What's the current enclosed inside the capacitor by surface S1? 0. There is no current going through. So it's mu naught times 0, which is 0. That tells us that the tangential magnetic field, B tangential, inside the capacitor must be 0. That's what regular Ampere's law tells us for surface S1. Let's take instead the spanning surface S2. That spanning surface S2 has also got the same boundary C. So we're going to be doing nothing illegal. Let's just choose some direction there. In doing the same process. So the left-hand side will still be the same, Bt times 2 pi r. And the right-hand side now is going to be mu naught times either plus or minus the current as a function of time, where I'm not getting too bothered about the plus or the minus sign. The main point I want to make is it's not 0. So on the one hand, you get 0, on the other hand, you get not 0. This is a contradiction. And when this was discovered, poor Maxwell had nowhere to hide, poor Ampere had nowhere to hide, and he didn't know what to do. It was a huge embarrassment, and people thought, wow, he goofed up. Well, Maxwell rescued the situation. He said, let's imagine that even inside the capacitor there's a current. It's a very outlandish notion. There's nothing inside the capacitor, it's a gap. So he said, let me define a current called the displacement current, I sub d. And that displacement current is defined as follows. It's epsilon naught times the rate of change of electric flux across the open surface that you're considering, whatever surface that is, whether it's S1 or S2. Well, let's define that. So let's phi e open is the double integral over the surface S of E dot dA. This is known as the open electric flux. Actually, Maxwell had completely independent reasons. He did not even look at this example. Maxwell's only reason for putting this displacement current, today it might seem like a miracle and an act of faith, but Maxwell was primarily a mathematician. He was not a physicist, and his primary love was mathematics and symmetry. So what he did was he actually examined the two laws of nature side by side. Now, by the way, let me just finish the story here. If you have I sub d defined like this, then of course the first surface S1, it's not mu naught times I 0, it's going to be mu naught times I sub d. And then when you work out the details, as I asked you to in that problem of the week, one of the problems of the week, then you'll find that the answer is exactly equal to I of t. So Ampere's law is finally salvaged if you add this to the right hand side of Ampere's law. So now the modified Ampere's law, let me write the new Maxwell Ampere law as it's called. And the new Maxwell Ampere's law is the circulation of B, which is integral of B dot ds, is going to be mu naught times I enclosed plus I displacement. With this understanding that sometimes the enclosed current is 0, the displacement current then kicks in. And if the displacement current is 0, then the enclosed current kicks in. Usually, in most problems, two of them never kick in together. There are some very strange, weird situations where they do, but in most problems that we'll look at your course's level, it'll be either one or the other. So Ampere's law is saved in this manner. So Maxwell Ampere law is a very huge achievement in the history of physics. Now back to the story of how Maxwell himself found it. He did not think about capacitors and all that. That's a way for us these days to explain to students why it's necessary. Maxwell had a completely weird and strange reason. He was a mathematician first and foremost. His argument was purely symmetry. He looked at Faraday's law on the one hand. It's a good idea for us to study the history of the evolution of human ideas sometimes, because that will tell us how to go forward when we are trying to discover new laws on our own. Okay, so it's good to study how people came upon these things. Faraday's law on the left, Ampere's law on the right. Now Faraday's law is absolutely correct. There's nothing wrong with it. Faraday's law says that the induced EMF, which is defined as the circulation vector, circulation of the electric field vector around a closed path ds, is going to be negative from Lenz's law, rate of change of the magnetic flux through the open surface divided by time. That's what Faraday's law has got. Ampere's law has got the circulation of the B field, which has got nothing special in terms of symbols, so I'll just write what it is. It's B dot ds about the curve C equals mu naught times the current enclosed. So let me write that part like that, J dot dA, and where here phi open B is going to be the double integral over the surface S, which bounds which the curve bounds of B dot dA. So this is the state of affairs here. What Maxwell was struck by is how different these laws look like. On the left side, you have a circulation integral of the electric field given by the rate of change of something that's changing with time. On the right side, you have the circulation again of the B field given by not the rate of change of something. It's just current density. It's a fixed thing. You put a battery, you have a current, you're passing it through a commercial wire, you have a current density, end of story. There's nothing changing with time. It's a steady state situation, and that's not a steady state situation. So Maxwell was struck by the asymmetry, and he believed, he had a very strong Scottish belief that nature does not play games like this. He thought that nature should be exactly symmetrical. And also during Maxwell's times, FYI, this mu naught, epsilon naught, etc. did not exist. At that time, the unit system used was called the MKS system. The other unit system used that time was called the CGS system. In these systems of units, you don't get these factors of epsilon naught or mu naught. You just get nothing you just get something like this, and there's nothing else except J. And here you don't get, when you define the displacement current, you don't get that epsilon naught. So Maxwell did not even have all these funky units that you have from SI to distract you. So he thought, okay, this cannot be. We need a better situation than this. What if I define something that looks like a rate of change? And that's where he had his brilliant stroke, where he added, instead of mu naught, he said, let that also be there because you need it. But what if there are no currents? If there are no currents, then you have this looking like this, and that is now 0 on the right side. Well, that doesn't look good. So I'm going to add to this something that looks like that. And why did I put epsilon naught? Because today we use SI units. Maxwell did not do that. He just said, here I have del phi B by del T. Here I'm going to put plus del phi E by del T. Now why he chose a plus sign and a minus sign is beyond the scope of this course. But he put that plus sign. And then it all worked out. And then he said, oh, wow, if I do this and I work in vacuum, as we'll see in the next video, he showed that light is an electromagnetic wave. So this implies that light is an electromagnetic wave. And that was his only motivation. He wasn't interested in charging a capacitor. Well, later on people said, hey, by the way, it also explains this paradox of charging a capacitor and things like that. But Maxwell's ambition was entirely symmetry, and that nature does not play games, so we should have this term. It's one of the most inspired things in the history of physics ever.